So when you look up at the night sky, maybe picture the very core of our own galaxy, the Milky Way. It's known to be this really chaotic, high-energy place. And for decades, astronomers have had this big question. How do stars even manage to form, let alone survive, in an environment like that? Well, today we're going to dive deep into exactly that. There's this fascinating new study out. It uses data from NASA's SOFIA Observatory, that's the Stratospheric Observatory for Infrared Astronomy, now retired, but the data is clearly invaluable. And it seems like this study is really changing how we think about star survival in these, well, extreme conditions.
Absolutely. And that's really our mission for this deep dive. We want to explore how magnetic fields, these huge invisible forces, aren't just, there. They actively shape the interstellar stuff, the gas and dust, and basically steer the evolution of the galactic center. And this new work, it's not just a small step. It feels like a major leap forward in understanding how these incredibly powerful magnetic forces operate in such an intense place, much more dynamic than we thought.
Okay, so let's get into the core finding then. The big news is the first high-resolution map of magnetic fields right in the galaxy's central zone, which immediately makes me ask, how on earth do you map something you can't see? Magnetic fields are invisible.
Right. That's the brilliant part. It comes down to tiny things. Microscopic interstellar dust grains.
Dust? Really?
Yeah, tiny sort of elongated grains. Think of them floating out there. When starlight hits them, they tend to align themselves with the local magnetic field.
Okay.
And as they absorb and re-emit that starlight, especially in the infrared, the light they give off is polarized.
Polarized, like with sunglasses.
Kind of. The polarization, the direction the light waves oscillate, it lines up with the dust grains, which are lined up in the magnetic field. So that polarized light acts like a unique signature by measuring that polarization very carefully across the sky.
You can trace the field lines.
Wow.
Making the invisible visible.
Exactly. It's really ingenious.
So they use this technique, they build this map. What did the magnetic fields actually look like? What structures did they find?
Well, this is where it gets really interesting. They found the magnetic fields aren't just random. They actually wrap around this huge expanding shell.
A shell.
Yeah, a shell of hot ionized gas plasma, basically. Gas that's had its electrons stripped off.
And what's blowing that bubble? What's making it expand?
That appears to be driven by incredibly powerful winds coming off a cluster of massive young stars located inside the shell.
Okay, so young, hot stars are inflating this gas bubble, and the magnetic fields are stretched around it almost like a magnetic skin.
That's a good way to put it, yeah. Containing it, shaping it.
Does finding this structure, this shell wrapped in magnetic fields, help solve any other cosmic mysteries we've had about the galactic center?
Absolutely. It points directly towards a puzzle that's been around since the 1980s, which these things called radiofilaments. Astronomers found these incredibly long, thin, thread-like structures near the galactic center. They glow brightly in radio waves, and we know they're beaming out electrons moving at almost the speed of light. But why they exist, how they formed, that's been a huge question mark.
Right. I remember reading about those, just these strange, unexplained threads.
Exactly.
Yeah.
And, well, this new magnetic field data offers a really compelling explanation.
Okay, so connect the dots for us. How does the map explain the filaments? What's the process?
It strongly supports a theory called magnetic reconnection.
Magnetic reconnection. I've heard that term in relation to the sun, haven't I?
You have. It's the same fundamental process we see causing solar flares. Imagine magnetic field lines pointing in opposite directions getting pushed together. They can become tangled, snap, and then violently reconnect into a new configuration.
And that releases energy.
A huge amount of energy.
Yeah.
And in the process, it can accelerate charged particles like electrons up to incredible near-light speeds.
So the idea is that where these magnetic fields are being stretched and interacting around that expanding shell.
Precisely. Where those fields get tangled or forced together, reconnection happens, and bang, you get jets of high-energy electrons, creating those filaments we see in radio waves.
Wow. So it's like we're seeing solar flares, but on a galactic scale, powered by these massive star winds interacting with the magnetic fields.
That's the picture this data paints. It's a powerful confirmation of this mechanism happening right in our galaxy's core, a kind of universal cosmic particle accelerator.
It really gives you a sense of this whole dynamic environment. You called it a cosmic ecosystem earlier.
Yeah, I think that fits. You've got all these different parts interacting, dense molecular clouds, the cold star nurseries, then you have the hot ionized plasma, like in this expanding shell.
And woven through it all are these magnetic fields we're mapping.
Exactly. And it's not static. It's a constant interplay, a kind of cosmic ballet, you could say. Forces are pushing and pulling. You have the outward pressure from the stellar winds, not just from the young stars, but potentially from even rarer supermassive stars called Wolf-Rayet stars.
Wolf-Rayet stars, right. Those are incredibly energetic.
Hugely energetic. So you have their wind pressure and you have the magnetic pressure, the tension in those field lines we mapped. And the balance between these forces dictates how the gas moves, whether conditions are right for new stars to form or maybe whether existing material gets dispersed. It shapes everything.
It's an amazing picture. But with any big claim like this, validation is key. How confident are the researchers in this map and this interpretation? Did anything else line up?
That's a crucial question.
Yeah.
And yes, they found some really strong corroborating evidence. They called the study a galactic Rosetta Stone for a reason.
Okay.
They compared their magnetic field map to data from a completely separate survey that looked at emissions from ionized carbon.
Ionized carbon, what does that trace?
It traces the very edges of these energetic regions, these bubbles of ionized gas. It's like a different kind of fingerprint for the same structure.
And they match?
Perfectly. The boundaries seen in the magnetic field map lined up exactly with the edges traced by the ionized carbon emissions.
Wow. So two totally different methods pointing to the exact same structure. That's pretty convincing.
It really is. It's strong, independent confirmation that they're mapping a real physical structure shaped by these forces.
And wasn't there something else? You mentioned Wolf-Rayet stars.
Yes. Adding even more weight, the team pinpointed a known Wolf-Rayet star, one of those rare, supermassive, windy stars located right near the center of this expanding gas bubble.
So the likely source of the powerful wind driving the whole thing is sitting right where the model predicts it should be.
Precisely. It fits the picture beautifully. A known engine right at the heart of the structure they mapped.
Okay, so the evidence for this happening in our Milky Way seems really solid. But what about further afield? What does this tell us about other galaxies?
That's the really exciting extension, isn't it? While, yes, this is a deep dive into our own galactic center, understanding these detailed interactions, the star winds, the gas dynamics, the magnetic field shaping right here in our backyard, gives us a vital template.
A blueprint, almost.
Exactly. A blueprint for understanding similar high-energy environments we observe in distant galaxies. When we see comparable structures or phenomena elsewhere, we now have a much better physical model based on what we've learned here.
So it helps us interpret what we're seeing across the universe, understanding their evolution, too.
It does. It allows us to decode what might be happening in the cores of other galaxies, places where star formation is also happening under extreme conditions. It's fundamental to understanding how galaxies evolve, how stars manage to ignite in these challenging places, and really how magnetism acts as this large-scale sculptor of cosmic structures.
It really shifts the perspective, doesn't it? Magnetic fields aren't just some passive background feature anymore. They're active players. Architects, like you said earlier, shaping how galaxies live and breathe. It's kind of mind-boggling to think about these invisible forces having such a profound impact.
It truly is. And it leads to that final big question, really drawing directly from the implications of this study. Could it be that understanding these magnetic fields in all their complexity is actually the fundamental key? The main missing piece we need to finally unravel the complete story of how galaxies like our own Milky Way formed and how they continue to change over billions of years.
A profound thought to leave us with. These unseen forces, perhaps holding the ultimate answers. Something for all of us to ponder as we look up at the cosmos. Definitely encourages you to keep exploring, doesn't it?